Okay, this is lecture 4 of our course. Last time we introduced two very important types of probability distribution, binomial distribution and Poisson distribution. And because they're so very important, I think it's a good idea to start with a little revision. So, binomial distribution. It refers to a series of independent Bernoulli trials with some constant probability of success P. And the probability of R successes, series of, n Bernoulli trials with a constant probability of success P. And the probability of R successes equals n, choose R, times P to the power R, 1 minus P to the power n minus R. And R can take on the values from 1 to n. And this is the Bernoulli, the binomial distribution that describes this Bernoulli process. Okay, Poisson distribution. With mean lambda. Lambda, it's the Greek letter that conventionally denotes the only parameter that is in this distribution, and the probability of occurrences of the observed event is e to the power minus lambda, lambda to the power r divided by r factorial. And unlike the binomial distribution, the list of possible values that R can take on in this distribution is infinite. It starts with a 0, but it never ends. Okay, when we introduced this Poisson distribution last time, we actually introduced it as a limiting case of the binomial distribution. And actually, we derived it in a mathematical way. So if the number of trials here approaches infinity and P approaches 0, so that lambda, that is n times P, is kept constant, this kind of distribution approaches this kind of distribution. Which means that if n is large and P is small, we can expect that the Poisson distribution, well, should be a good approximation to the binomial distribution. Let's discuss an example of this. Okay, a certain company is engaged in mailing out catalogs. It's selling furniture by catalog. So mailing catalogs. Okay. Well, the efficiency of this procedure, the efficiency of this kind of trade, mailing out, is not very high. Let's say that 1.5% of the time, a catalog that is sent out brings a sale, results in a sale. Okay, so 1.5%, the company gets a sale in response to mailing a catalog. Suppose 100 such catalogs has been sent out. What's the probability that the company gets exactly 2 sales as a result? So 100 catalogs And what's the probability of 2 sales? Okay. Well, now please notice that the probability of success on each trial, and we interpret each catalog that is sent out as trial. The probability of success on each trial is small, and the number of trials is rather large. So we can expect that the Poisson distribution can be a good approximation to the exact distribution, which here is the binomial one. Okay. Now let's do it twice. Let's apply the exact formulas of the binomial distribution, and then we'll see what Poisson distribution gives us, whether the two answers are close or not. All right. Now, in the Poisson distribution, I'm sorry, in the binomial distribution, so binomial, the answer is this. 100, choose 2, times the probability of success, which is this, okay, raised to the power 2. And then the probability of failure, which is this, is raised to the power 100 minus 2, which is 98. And the answer that we get here to 3 decimal figures is this. Okay. How do we use the Poisson distribution as an approximation to this? The only thing we need to compute is lambda, the mean, which is the product of n and p. So lambda is 100 times this, and it's 1.5. Okay. And now we use this formula. The probability of 2 successes, or rather 2 occurrences of this event in question, is e to the power minus 1.5, 1.5 to the power 2 factorial. Okay, and the numerical answer is 0.251. Okay, if you compare this and this, you'll see that the 2 answers match to 2 decimal figures, good enough for practical purposes. So the conclusion here that we can make is this. Poisson distribution can be effectively used as an approximation to the binomial distribution if the number of trials is large and the number of successes, the probability of success in each trial is small. Actually, Poisson distribution was first described sometime early in the 19th century, and for about a century it was used in exactly this way as an approximation to the binomial. But later, rather late in the 19th century, it was noticed that actually the application of Poisson distribution is wider than that. It doesn't have to be treated as an approximation of some binomial distribution. Okay, it goes outside this narrow model. Let's talk about Poisson distribution in more general terms. So here it's a general view of this distribution. Now, Poisson distribution generally describes the number of occurrences of a certain event in a given time interval or spatial region or something. So, number of occurrences there is an accepted term here. These occurrences of this observed event are called arrivals. So when we use Poisson distribution, this word is conventionally used. The number of occurrences or arrivals of a certain event per given time interval or spatial region. Okay. Well, typically, the events that we register, that we observe, may come from any of a great number of different sources. And these sources, well, first, there are a lot of them, and second, the probability that for any given source, the probability that this particular source will create the event in question per given time interval is small. Okay, this is a bit vague, but if you think of the two examples that I used when I first introduced this distribution, I hope this idea will become clear. Do you remember this cake example? We had 200 raisins, and those raisins were distributed in a random way over the volume of the cake. So these, and then we look at a particular volume of 1 cubic inch and record the number of raisins that get into this chosen volume. Now, if we reason in these terms, we can say that the appearance of a raisin in this given volume may result from any of the 200 raisins. So we have 200 possible sources of this event. Okay, there are a lot of sources, but the probability for each of them in particular, for each of these raisins in particular, the probability of getting in this chosen 1 cubic inch volume is small. Okay, and the other example was about a town that has 2,000 residents and only one dentist. And also in this example, we can consider these 2,000 residents as sources of visits to the dentist. Okay, there are lots of residents. Well, 2,000 is not a large town, but in terms of probability theory, 2,000 is a lot of potential sources of this event. And for each of them, the probability of visiting the dentist on a particular day is very small. Okay, this is what I meant to say here. Let me not write this any further. I hope you understand what I mean. But when I say that here we want to talk about Poisson distribution in more general terms, what I mean is this. In the examples that we've discussed so far, it was clear what the underlying binomial distribution was. Okay? We could describe it mathematically, but quite often the underlying binomial distribution just doesn't exist or is difficult to describe, and still we work with the Poisson distribution. Now let's see how it works. Example. Well, let's look at the number of emails somebody, well, say me, the number of emails that I get, that I receive per day. Number of emails. Emails per day. Well, I don't have a lot of correspondence. I don't get very many messages. Well, roughly, if I think of it roughly, the mean may be something like 3. Okay, let's say that is 3. Okay. Now, let's look at what's written here. Can we say that the appearances of this, the arrivals of this event are independent of one another? The arrival of one message is independent of the arrival or non-arrival of another message. I think it's a very natural thing to assume. They arrive independently. Well, we may make some reservations here, because sometimes one message follows another message for some logical reasons, okay? Well, let's neglect these subtleties. So let's assume that email messages arrive or do not arrive independently of one another. And this is the mean arrival rate, 3 messages per day. Then we can use the Poisson distribution, although it's difficult or maybe impossible to define the underlying binomial distribution. If I only had a very definite list of correspondents, say 30 correspondents, and each sent me a message once in some time interval, then we could talk about a binomial distribution. But the list of correspondents typically is not very defined, okay, very well defined. It's kind of has blurred, indefinite boundaries. Some people write me just once, okay, on some special occasion, and never write anymore. And also, as anyone else, I receive a lot of advertising that comes from indefinite sources that I don't know, I don't want to know, well, things like that. What I want to say here, we cannot really define in any clear way the underlying binomial distribution, and still we can hope that the Poisson distribution is a good way to describe this process. Okay, actually, you can do some experimental work at home. Look at your email box and count the number of emails that you get over some period of time, such as, well, a month. And compute this. And then use the Poisson formulas to get the probabilities that you get no messages at all, 1 message, 2 messages, 5 messages, and compare with the statistics that you get from your own email box. Let's see whether Poisson distribution works well in your case. Okay? Well, if it works well in my case, then, for example, the probability of getting exactly 2 messages on a given day is this, and it's 0.224, and the probability of getting no messages at all, okay? Generally, it's e to the power negative lambda. So here it's e to the power negative 3, which is, okay, it's interesting. So with this arrival rate, 3 messages per day on the average, 5% of the time I'll be getting no messages at all. It's interesting. And accordingly, the probability of getting at least 1 message on a given day is 1 minus this, which is 0.95, okay, like this. Well, so I discussed this example specifically for the purpose of underlining that the binomial distribution is not a necessary condition for us to use a Poisson distribution. Well, another example like this. We can record during a rain. We can look at a particular area of the ground and record the number of raindrops that fall on this chosen area per unit time. Say, well, it's if per minute, per second, whatever. And well, actually, actually, Poisson distribution can be expected to work very well for this natural process. It works very well. It works very well for natural processes such as radioactive decay, particles that come from outer space, things like that. And raindrops is also a very good example. Well, I don't expect you to perform any real experiments, and we don't have any rain in this time of the year. But believe me, this is a good example of a case in question. All right, but when we look at raindrops, there is no way we can define the underlying binomial distribution. Okay, we cannot list the possible sources from which these raindrops come. It's just impossible. Okay, let's look certain event interval occurrences. Well, independent. I didn't write it here explicitly, but I said that we assume that these the arrivals of this event are independent of one another. And this is an important condition. If you use the Poisson distribution, you should take care that this condition is satisfied. As a little example, let's discuss this situation. Suppose we are interested in developing the probability distribution for the number of customers that visit a small restaurant. Suppose a small restaurant that suppose has as many as 10 tables or 15 tables. Okay, a small one. Now, and we record the number of customers that are in this restaurant at a given point in time. Okay. Now, what do you think? Is it a good idea to use Poisson distribution here? Or maybe there is something that is not, a condition that is not satisfied in this situation. Anyone? Well, I wanted you to notice that here we cannot expect independence. People do not generally come at restaurants one by one, independently of one another. They come in pairs or in larger groups, which is much more typical than people coming individually. At least, well, I have a very limited experience with restaurants, I must say, but this is my idea of a restaurant. People come in pairs and in larger groups. If I'm right, then the Poisson distribution will probably not work very well for this problem. All right. So much for binomial distribution and Poisson distribution. If we have time by the end of this lecture, I'll get back to this point and discuss something else. When we write these formulas that are not here any longer, the formulas for the binomial distribution and Poisson distribution, mathematically speaking, before we start applying them, we need to make sure that they are consistent in the sense that the probabilities, well, in the binomial distribution, the possible cases is 0 successes, 1 success, up to n successes. Now, if we sum up all these probabilities, we expect that the sum is 1. Otherwise, it's not a valid probabilistic model, okay? And yes, the answer is yes, the sum is 1. And the same is true for the Poisson distribution. And in the Poisson distribution, this sum is infinite. It's an infinite series. And if we have time later on, we'll get back to this point and see how these consistencies can be proved. All right. The next big chapter in our course is random variable. Well, at the very start of this course, I said that a probabilistic model starts with defining the sample space. And it's true. It's always true. But quite often, we are not interested in the outcomes as such, but in some numerical values that are associated with these outcomes. Okay? Then we talk about a random variable. Random variable, well, let's use this abbreviation for random variable because I can't write it again and again. Random variable is a variable whose values are subject to chance. Well, this is a meaningful definition, but not a very mathematical one. A more mathematical, a more technical definition is this: a random variable is a function defined on omega, which is the sample space of a given experiment. So, if we define a numerical value for each outcome in the given sample space, what we get as a result is a random variable. Okay? And mind you that random variables is the main object of interest and the main object of study in probability theory. Well, let's start with this classic example, the simplest possible example, probably the experiment of rolling a die. Rolling a die. Well, in the classical die, there are 6 faces, and there is a number printed on each face. So when we roll a die, there is always a number on top. The die turns up 1 or turns up 2, up to 6. In this way, well, we don't have to do anything to associate outcomes with numbers. The numbers are already there. So the random variable has values. The possible values are 1 to 6. One value per outcome. Okay? Now, this is the simplest example, but it's not at all a general type of random variable. Let's discuss a slightly more realistic example. Now, suppose we select one person at random in this room and find out the age of this person, say in complete years. Okay? Now, just let me do some asking just to get an idea what values are possible. Is there somebody in this room who has the age of 17, age 17? Are there any such people? No, too young. 18? Someone. 19? 20? 21? Okay, I think you're a bit older than that. 28. And there is one person who is really old, 59, which is your obedient servant. So if we pick a person at random, the answers will be 18, 20, 21, 28, and 59. And that's it. No other possible values. What do I mean to say by this example? The number of possible outcomes here is equal to the number of people present in this room. But the number of possible values of of the random variable defined in this way is much smaller. It's only five different values. Okay, so please keep this in mind. The number of the set of outcomes doesn't have to be in one-to-one correspondence with the set of possible values. Okay, the list of values typically is much shorter. This is point 1. Point 2 is this. We can define the random variable for the same sample space in a different way. Suppose we can record the ages not in complete years, but in complete months, which will give us a much longer list of possible values. Okay? Or we could be interested in a different random variable altogether, such as body height or body weight or something, or girth, something else. Okay, so for this, what I mean to say, for the same sample space, for the same physical random experiment, we can be interested in a different random variable. It's up to us how we define it. There isn't a definite unique correspondence between sample space and the random variable. Random variable is something that we introduce on top of it, on top of the sample space. Okay, next. the simplest and probably the most important random experiment in all probability theory is this Bernoulli trial, which is illustrated typically by tossing a coin. It becomes a random variable if we define numerical values for the two possible outcomes. And typically it's done this way. Heads is associated with number 1 and tails is associated with number 0, or the other way around. It doesn't really matter. So one of the outcomes is 1 and the other is 0. If it's about a coin, generally success is 1 and failure is 0. So here we do not have these two numbers well, in some natural way in this experiment. We need to introduce these numbers. Okay. All right. In a binomial distribution, binomial. Well, and one more thing. Typically, the accepted way to introduce the probability distribution of a random variable is by means of a table. And for this simple experiment, the table is also quite simple. Well, can you see it here, or shall I write it somewhere? So first, we list the two values that this random variable can take on. It's 1 and 0, 1 and 0. And then we enter the corresponding probabilities. And it's P for success and Q for failure. And this is a complete description of this random variable. Now let's give a description of this kind to the binomial distribution. Let's say that the probability of success on each trial is P, and there are n trials. Now, what possible values does this? Well, if we define the value of the random variable here as the number of successes on n trials, number of successes on n trials, then the possible values are 0, 1, up to n. And the corresponding probabilities are, well, what's the probability of getting no successes on n trials? Well, the probability of success is P, so the probability of failure is 1 minus P. There is a separate notation for it, it's Q. So the probability of getting n failures in a row is Q to the power n. Well, then it's n, choose 1, P to the power 1, Q to the power n minus 1, and so on. We use this formula for the probability for the binomial distribution, and the last entry here will be P to the power n. Okay. Well, what about Poisson distribution? No, before we get to Poisson distribution, let's define a different, we still look at this process, Bernoulli process, n Bernoulli trials in a row, performed in a row. But we can define a different random variable here, and actually it's not something artificial, it's important in some applications. It's called geometric distribution or geometric random variable. Let's ask this question. Suppose we perform this Bernoulli process. Well, this time, here we say in advance that we are going to perform n Bernoulli trials. Suppose we do not set any limit for the number of trials in advance. And let's say this, that we look at the first success. We're interested in the first success that occurs in a row of Bernoulli trials. And the value and the random variable is defined as the number of the trial on which the first success occurs. The number of the trial of the first success. Okay. Now, and this is called geometric distribution. Well, can a success occur on the first trial? Is it possible? Well, yes, obviously, and this is the probability of this event. So 1 is a possible value, and the probability is p. Well, can the first success occur on the second trial? And what's the probability of this? Now, for the second trial to be the first successful trial, the first trial must be unsuccessful. Okay, so for this to be true, the first trial must be unsuccessful, like this. And the second trial must be successful. Okay? And how can the first success occur on the third trial? Then we must have 2 failures in a row and then a success, which means that it's q squared times p, and so on. Okay? And okay. The kth trial is the first successful trial if the k minus 1 previous trials are failures, and then the kth one is a success, and so on. And potentially, this row never ends. It's potentially infinite. Okay? So it's called geometric distribution. It's something new. We haven't discussed it before. All right, Poisson distribution. And accordingly, we talk about a Poisson random variable. And the values, the possible values in this kind of variable, well, the value, the random value here is the number of occurrences of the event under observation. And we can have no arrivals, no occurrences. Say the mean is lambda, then it's e to the power minus lambda probability, okay? And for k occurrences, it's e to the power minus lambda, lambda to the power k, k factorial. And as in the previous example, this row never ends. We have an infinite row of possible values here. Okay. All right. Now, all the examples of random variables that I have mentioned so far refer to the case, to the category of discrete random variable. Definition. Discrete random variable is one that has a finite or countably infinite set of possible values. Well, something is not quite clear here. What is finite? Finite is okay. Now, binomial distribution, binomial random variable has a finite set of possible outcomes from 0 to n. A Bernoulli trial, just one Bernoulli trial, has a finite set of possible outcomes, possible values of the random variable 0 and 1. but what is countably infinite? The examples of these are provided by Poisson random variable and the geometric random variable that I discussed earlier. Now, a set can be finite or infinite, but infinity may be of various, well, there are more than one kind of infinity, so to say. Some sets are countable infinite. A set is called countable infinite if its element can be arranged as a list, okay? And this is the case for Poisson distribution and geometric distribution. But there are also infinite sets that cannot be listed, cannot be counted. So there are countable and uncountable. This is not a very not simple stuff. Okay, this refers to the theory of sets, theory of number sets. I'm just mentioning this. Okay, the simple way to understand it is this: if the set of possible values of a random variable is infinite, but such that it can be arranged as a list, then it's still called a discrete random variable, and it's supposed to be a simple case. All right. Now, generalizing from the examples that we discussed so far, a discrete random variable is introduced and described by giving the probability distribution. Distribution. Well, this is a general term. For a discrete random variable, the probability distribution takes the form of the probability mass function. Probability mass function. Okay, and there is this accepted abbreviation PMF, probability mass function. Well, this is a very simple concept. The probability mass function for a random variable is defined through a table of this kind. We list the possible values. It can be a finite list or an infinite list. And the second row gives us probabilities. Okay? Okay, like this. By the way, there is a convention about notation. Capital Latin letters are used to denote the names of random variables, and lowercase letters are used to denote specific values. And it works very well in a textbook, but when I write on a board, it's not always easy to distinguish between the two. So this is my attempt to show a capital letter, and this is my attempt to show a lowercase letter. Well, I think these two can be distinguished well enough here, because I specifically made an effort to make them different, but I'm not always as successful in doing this. All right, so this is what is called PMF, probability mass function. It's just two corresponding lists, the list of possible values and the list of corresponding probabilities. Okay, if we want to give a visual representation of it, then the simple picture is this. Well, we either represent the probability as dots, like this, or maybe as vertical segments, line segments, or bars, like this. Okay, probably this second approach is more popular. Well, I don't see if it's any better than just giving the probability as numbers. Well, there is an alternative way to define the probability distribution, and this alternative way relies on the so-called cumulative distribution function. Well, cumulative is a formal word, a bookish word. Cumulative means, well, cumulative refers to the result of aggregation or gathering of some kind. There are, by the way, cumulative clouds. Okay, this term in weather talk. All right, what is this about? The accepted notation is F capital, and by definition, for any x, the F capital is the probability that the random variable takes on a value that is less than or equal to this specified little x. Okay, so here x capital, the name of the variable, and little x is a specific value. And this is the definition of the cumulative function. All right. Now, what is the difference between this instrument, this way of describing a random variable, and the PMF, probability? By the way, there is this CDF, cumulative distribution function, and this is PMF, probability mass function, accepted abbreviations. Now, are there any advantages in using this rather than that? Well, so far as we are talking about discrete random variables, cumulative distribution function doesn't offer any real advantages. Let's look at the graph. Okay, like this. Well, if we talk in terms of graphs, it's important to understand that the PMF, probability mass function, is only defined at separate points. It's not defined anywhere in between. The cumulative distribution function is defined everywhere for any x, and this is the definition. Well, but because all the probability in a discrete random variable is concentrated at some specific points, the result for the cumulative distribution function is that it's not continuous, it's not smooth. It experiences breaks. Actually, it's like this. If x1 is the leftmost possible value, then F capital is exactly 0 anywhere to the left of this. And then there is this jump, okay, this jump. The size of this jump is exactly equal to this probability, okay? And then we again have a horizontal segment up to this next point. So this point doesn't belong to the graph. We represent it by a hollow circle or an arrow, and this point does belong to the graph. And again, no point here, jump, point here, and so on. And the size of this other jump is equal to the size of this probability. Okay, so this cumulative function consists of horizontal segments separated by jumps. Now again, what's the use of introducing this additional instrument that doesn't seem to give us any real advantages? The real advantage is this. Just very shortly, we are going to introduce a different class of random variables, in continuous random variables. And for continuous random variables, this is not possible. But this definition works equally well for continuous and discrete random variables. It's more general. So its real advantage is that it's more general. It can be applied to any random variables. All right. Now let's talk about expected value or expectation. Okay, expected value or a shorter term is this expectation. Sometimes they say mathematical expectation to emphasize the mathematical nature of it. Now, what is this about? Quite often, we don't really need to know or to use the probability the distribution of a random variable in all its details. Quite often, we are not concerned about all the details of this distribution, and we are satisfied with knowing some summary, some parameters that summarize all this distribution and give us an idea of the main properties of the distribution. Okay? And the most common and the most widely used parameter of this kind is this, expected value. Now, what is this about? What question does it answer? Expected value answers the question, what is the given random variable centered about? What is it distributed, what point, what value is it distributed about? Okay? Loosely speaking, what is the center of the distribution? Center. Okay? Well, just as a little example, suppose we conduct a survey aimed at finding the distribution of individual incomes in a certain area. Okay? Say monthly incomes. And the result is a great, huge pile of data, okay, that we obtain from this survey, field survey. Well, and we bring it to after a lot of labor that we invested into this. We bring this pile of data to our superior manager, and we expect to be rewarded for this. And the manager says, don't bother me with all this data. I don't have time to look into this. Just give me the expectation. What's the mean or expected value? Just give me one number. Okay? What is this distribution centered about? What's the center? And you understand that, well, I don't know how to describe the feelings of an employee in this situation. Maybe feelings of deep satisfaction, I don't know. All right, anyway, so what's the center of the distribution? We compute this parameter on the basis of the detailed distribution. We kind of compress the data, convert them into one parameter that, in a certain sense, describes the entire distribution. Okay, now what's the definition? First, this is the notation, capital X, then square brackets, and the name of the random variable. And it's the sum that is taken over all the possible values that can be taken by the random variable. And each time we multiply the value by the corresponding probability, and then we sum up all such products over all the possible values. Okay? Well, there is an alternative notation. This. Now let me tell you that this E, capital E, is more typical for probability theory, and mu here, mu is a Greek letter, is more typical of statistics, or at least it used to be this way. But now, because the two sciences kind of merged, integrated, this term is also widely used in probability theory. So E, expected value, and mu is the same thing. And when we use this symbol, we can also use this term, mean, in the same sense, in the sense of expected value. All right, also, this verbal explanation or description is often suggested. Expected value is a measure of central tendency or location. Well, I'm not sure it's a very good way to explain it. Well, so far as I'm concerned, I don't find that it's a very a very fortunate way to explain it. The idea of the center of the distribution appeals to me more. All right. Now, let's look at this again. We can, from the mathematical point of view, we can consider this as a weighted average. Weighted average. In this weighted average, the values of x, the possible values of x, are averaged with the corresponding probabilities used as weights. Are you acquainted with the concept of weighted average? I hope you are. Then these are the weights here, okay? And because the weights here are all positive, being probabilities, and sum up to 1 being probabilities, we can conclude this is simple algebraic stuff. I just don't have time to go into details. Just let me give you a conclusion. Because it's a weighted average where the weights are all positive and sum up to 1, the resulting value here cannot be larger than the largest of the possible values and cannot be smaller than the smallest of them. It must be somewhere in between. Okay? Also, sometimes an analogy from mechanics is used. Okay? When in a mechanical system we find the center of the mass, we do something like this. We do something very similar to this operation. Okay? So in a sense, that this is a center of the mass. All right. Now let's do something else here. We are going to develop a kind of justification for this, and it's really interesting and it's important. Very early in this course, I mentioned that there are 3 possible ways to introduce probabilities. The first being the classical model, and the second being experimental approach. Now, suppose we work within this second approach, experimental approach. Which means that we perform the same random experiment again and again many times. So we perform the same experiment is performed n capital times. Okay, I'll have to continue there. Suppose the values of the random variable that are observed in this series of experiments are x1, x2, and so on. Okay? And the corresponding frequencies, that is not relative frequencies, just frequencies, then the respective numbers of occurrences of these values are f1, f2, and so on. Okay, and obviously n capital equals the sum of all these frequencies. Okay, n capital is just split between the various frequencies. Okay, question: if n capital experiments like this have been performed, what's the average value observed? Now, average in my question is just good old arithmetic average, as we know from school stuff, and well, it's applied anywhere. Just arithmetic average. Let's look at this. This value x1 was observed this many times, and the second value was observed this many times. Now, what's the sum of all the values observed on n capital experiments? It's f1 times x1 plus f2 times x2 and so on, plus f, well, I don't know where to end this. Just we write it as many terms as the number of different values that we observed. So this is the sum of all the values that we observe. Do you understand this? This value was observed this many times and so on. And if we divide it by n capital, we'll just get the arithmetic average of this. Okay? And now let's assume that n capital goes to infinity. We can rewrite it this way. f1 over n capital times x1 plus f2 over n capital times x2 and so on. And I hope you recognize this. These are relative frequencies, and if n capital goes to infinity, then we associate these, the limiting values for these fractions are associated with probabilities. This is the experimental approach of getting probabilities. Okay, so this will approach p1 times x1 plus p2 times x2 and so on, which is exactly the definition of expected value. So if we apply the concept of arithmetic average to this repeated experiment, what we get in the limit is the concept, is the definition of mathematical expectation as is given there. Okay? Well, some simple examples. Rolling a die. Rolling a fair die now. Okay, I'm not writing this, just we always assume that the die is fair. Now, what's the expectation in this experiment? It's the possible values are 1 to 6, and the probability of which, if the die is fair, is 1 over 6. So it's 1 times 1 over 6 plus 2 times 1 over 6 plus 3 over 6 plus 4 1 over 6 plus 5 1 over 6 plus 6 1 over 6. Okay? And honestly summing up, this is what we get, 3.5. Now, when you first see this kind of answer, you may be a bit surprised that it's not an integer, not 3, not 4, it's 3.5. So when you roll a die, you can't possibly get this. You can get 3, you can get 4, you can get 5, but you can't get 3.5, which is on a linguistic level, it's in contradiction with this term here, expected value, or at least you may see a contradiction here, because actually we cannot expect to get this value in the experiment. Okay, this value is just impossible. It's a kind of mean value. This is correct. This is a correct interpretation, but exactly this value can never be obtained. Okay. Well, tossing a coin, our favorite experiment. Tossing a coin, not necessarily fair coin. What's the expected value? Okay, this is E. And here, now if we associate 1 with success that has probability P, and 0 with failure, which has probability 1 minus P, then it's 1 times P plus 0 times 1 minus P, and this is just P. So the expectation in this simple experiment is just P. All right. Now, what is the expectation of a series of the random variable that is distributed by the Bernoulli law? So, expectation in a series of n Bernoulli trials. Okay, so it's the binomial distribution. All right, without proof, let me say that this is expected value. Okay, well, it can be worked algebraically, but it's a bit messy, and we really can't afford going into this proof. Well, there is nothing counterintuitive in this formula. The expected value on one Bernoulli trial is p. On n Bernoulli trials, it's n times larger. For the geometric random variable, and geometric was something that I defined today, just a bit earlier, the expected value is equal to 1 over p. Well, let's look at this answer here. If p, the probability of success, is a small number, say 1/10, then the probability, then the expected number of the trial on which the first success occurs is a large number. So if p is 1/10, then the expected value here will be 10. Loosely speaking, informally speaking, we can expect that the first success will occur somewhere around the 10th trial. It's not a correct way to say this, to explain this, but just to try to understand it intuitively. All right, if p is 1/2, which means a fair coin, the expected value is 2. So the mean value of trials we need to perform to get the first success for a fair coin is 2, which is again quite intuitive, okay? Well, and for a Poisson distribution with mean lambda, the expected value is lambda, which is absolutely intuitive. It is to be expected because lambda was introduced as the mean number of occurrences in this experiment anyway. All right, so these are just some examples of expected value. Now let's talk about how this concept can be applied in practice. Actually, the concept of expected value quite often is used in decision making. Okay, it's a practical thing. Let's discuss an example. Okay, using expected value in decision making. We'll discuss just one example, although this is a broad area. Actually, it's an important and broad area. But we'll discuss just one very primitive example. Well, suppose a certain person, let's call her Jane, plans to open a business of her own. Specifically, she plans to open a beauty parlor. Okay, she has some reasons to believe that a beauty parlor can work successfully in her neighborhood. Okay, people are kind of in need of these services that a beauty parlor can provide. All right, now after she has searched for opportunities, she discovered that there are 3 options for her in terms of available to her, in terms of premises for rent, business premises. So there are three office of business premises. Okay. Now, but these three versions of three office of business premises are all of various sizes. If she takes one of the office, then she can only open a small parlor. Well, if she takes another offer, she can open a medium-sized parlor. And the third option means a large parlor. Okay. Well, obviously, opening a large parlor means larger expenses. Okay, but also if business goes okay, if it goes well, if it's successful, she can get larger profits in this case. Okay, so it's a kind of gambling situation. Now, Jane consulted some experts, and experts pointed out to her that the success of her business will depend crucially on the economic conditions and the state of the industry, not only on her efforts and skills, but there is this factor that is outside her control, the state of the industry. Okay, and with the help of the experts, of consultants, she developed this table. So, good market, fair market, and poor market. Okay. Well, experts came up with some probabilities. It's just expert estimates. It cannot be proved in any rigorous way. But the experts say that in the few coming years, she can expect good market for this kind of business with probability 0.3, and fair market with probability 0.4, and poor market with probability 0.3. These are expert estimates. Okay. Now, if she runs a large parlor, then under good market conditions, she will make this kind of profit, okay, in some units, probably in $1,000 or in 1,000 euros, whatever. Under fair market conditions, her profits will be 600. And under poor market conditions, she will actually make loss. She'll incur a loss of 500,000. All right. Well, for a medium parlor, the figures are 900 here, 400 here, and 200 here. And for a small parlor, it's 500 here, 400 here, and 300 here. Okay, if you look at these figures, you'll see that, well, it stands to reason. If the market is good, then the large parlor brings the maximum profit. But on the other hand, if the market is bad, the large parlor is hit the worst, okay, of them all. On the other hand, if she only opens a small parlor, she cannot hope to get a lot of profit, even on the good market. The business is just too small. On the other hand, it's more stable, okay, because the initial costs are not so large, so it doesn't mean losses in the end under any conditions. All right. So, given these figures, what choice should she make? Well, look at this title. Using expected value in decision making, we can use, or at least try to use, expected value as criterion that distinguishes among the options here. Okay. Now, what is expected profit. What is the, assuming these probabilities, assuming that these expert estimates of probabilities of the various states of the market are good, are sensible. What is the expected profit for this option here? Well, it's simple enough. We multiply 0.3 by this, 0.4 by this, 0.3 by this, and add up. And this is what we get, 450. And we get 490 here and 400 here. Well, what should Jane choose? If she relies on this criterion, then this is her choice. 490, medium-sized parlor, okay? Well, and let me tell you that this criterion is actually used quite often in business practice because it's quite convenient, it's easy to use, it's very technological, well, and quite convincing too. But we must make some reservations. Expected profit as criterion is not always what we need to use. Look at this Jane situation, beauty parlor situation. Okay, this is the largest expected profit, but this is the largest business, and many business people are sensitive to the size of the enterprise, because apart from the pure monetary value that they get status. Jane may be interested, Jane may be an ambitious person in terms of status. She may be interested in being a big-sized businessman in her community because this means big parlor, okay? She may become an important person in the local industry, in the community, okay? This big industry may mean connections with other businesses, influence, and so on. Well, which is not taken account of here, okay? In this computation. This is point one. Point two, this is about profit. But apart from the absolute value of profit, quite often we're interested, or business people are interested in the rate of return, not just the absolute sum. Do you understand this? It's a different story. This may be the maximum, the largest expected profit. And what is the expected return on the invested capital? Okay, it's possible that Jane is after that too. She's interested in getting the maximum rate of return, which means a different column and different computations. Okay. Well, also, while I am at it, let me suggest two more examples to you. I think it makes sense because let me tell you that this principle, this criterion is quite often abused. It's given too much credit. Actually, in real world, the application of this criterion is quite limited. Let's discuss this example. You toss a coin. Well, somebody approaches you with this suggestion. Let's toss a coin. If you win, well, if you lose, you pay me $100. If you win, I pay you $200. Well, what do you think? Is it a good suggestion? Would you take part in this kind of game? Well, if you apply this approach, absolutely, your expected profit is positive on this game, which means that you should take the offer. It's an offer that you can't refuse, as was said in one American novel. All right. Well, now, this said, suppose somebody, or maybe the same person, the same con artist, approaches you with a different suggestion. He says, okay, let's toss a coin once more. If you lose, you give me all you have, your business, your bank accounts, well, your jacket, and your car, and whatever, and your dog. So you give me just everything you have. if you lose. And if you win, I give you twice more of everything. Two cars, 2 apartments, 2 dogs, and twice of everything. Twice as much of everything. Now, do you understand the condition? So it's the same, basically the same game. Mathematically, it's the same game, just scaled up, multiplied by a huge factor. Well, let me tell you that no sensible person would play such a game. If it's all you have, it's about your only apartment, your only, your possessions, your last possessions, nobody will rise to such an offer. And what's the difference? Why does it look quite attractive to play this game on a small scale, and not so attractive on a large scale? Now the reason is this: if you lose $100, it's not the end of the world. Okay, if you win $200, you just win. But if you lose your apartment and everything else that you have, it is the end of the world for you, okay? You cannot go on with this game. This is the catch. If you were able to go on playing, you would win finally, with certainty. But if you lose everything, you can't go on. And it's a very poor consolation to know that if you had won, you would have twice as much of everything. Okay, it's no consolation if you lost everything and actually become homeless and pauper. All right, I hope I gave you some idea of why this criterion alone may be inadequate. And one more example of this. Quite a lot of people buy lottery tickets. And what do you think? What's the expectation on a lottery ticket? Is it positive or negative for you? Well, well, absolutely negative, of course, because the organizers of a lottery collect more money than they pay out. Otherwise, they would not be in this business, okay? So, for any person who buys a lottery ticket, the expectation, well, taking account of the money paid for the ticket and the possible gains and the probabilities, the expectation is negative. And everybody knows that. Everybody knows that the money paid, the total money paid out as prizes are less than the total money collected for these tickets. And still a lot of people buy tickets. Why is that? Again, this criterion doesn't work, but in the opposite sense. Negative expected value, and still people rise to the bait. And why is that? Because they, apart from expected value, they get something else. They get the excitement, the hype. They can be hopeful. They can hope for a big prize for some time at least. And this is something that has no monetary value. Okay? It's an additional benefit of some kind. Okay. All right. I think I've given you enough examples of. On the one hand, well, the examples that I cited here do not at all mean that expected value should not be used as a tool for analysis in decision making. Absolutely, it is a tool. It is a useful tool, but it should be used with caution, and the results of this kind of analysis should be considered along with a lot of other considerations that sometimes are much more important than just expected value. Okay, and I think that's all the time that I have today. Thank you. See you next time.